So let's do the magnesium plus the zinc nitrate. All right, so there's a couple things that would go, that doesn't say zinc nitrate. We've got magnesium plus what?
Nickel nitrate.
Nickel nitrate. Does everybody agree?
Yes.
You're wrong. It's not nickel nitrate. Nope. NO3 is nitrate, Ni is nickel. That does not make it nickel nitrate. What's the issue? Okay. We have to specify the charge if we're not required to memorize the charge. Is nickel one that we're required to memorize the charge on? No, which means when we write out the name, it must be nickel, Roman numeral, 2 nitrate. That gets named nickel 2 nitrate. You can't call it nickel nitrate. So just a little bit of nomenclature review there. So in doing our single replacements, we're required to be able to predict. We have the general form provided to us. Remember, I color-coded my general form where the blue ones are the cations, the positively charged species. The red ones are the anions. Okay. Single replacements, you can do single replacements with anions, okay, with the negatively charged species. For the most part, it is the cation that does the single replacement. Okay. So if we take a look at our reaction, we're matching our form for the single replacement. We just need to exchange. Okay. So the magnesium and the nickel exchange places. So the nickel now becomes a solid plus the, what was it, magnesium bonded to the nitrate. When we run our replacements, what we need to do is just draw out what our products are and then evaluate if we've done them correctly or not. Okay. For our single replacement, we're taking whatever was an ion and we now make it a solid. We put it into its elemental state. And we'll look at oxidation states here in a second. Okay. The magnesium then exchanges for the nickel. Okay. Notice I've written NO3. I did not write NO3 2. Why not?
Charge.
Why is there a 2 in nickel 2 nitrate?
Balancing.
Okay. The 2 in nickel 2 nitrate, that red 2, is to balance the nitrate with the nickel. Is the nitrate with nickel anymore? No. So I cannot use that 2. Okay, and this is where things are going to go really fun and sideways on us because you're going to be like, but. No, but. That red 2 does not show up in the product. Okay. What is the charge on magnesium? Magnesium is a +2 charge. What is the charge on nitrate? It is a -1. How do you know the charge on both the magnesium and the nitrate? Magnesium, you can cheat and use the periodic table, or you can cheat, well, it's not really cheat at that point, have it memorized. Nitrate, you have no option. You have to memorize the charge on nitrate. That is one of the elements that you're required to memorize, or polyatomic ions. And you're required to memorize that it has a -1 charge. So is that formula correct? No, because it hasn't balanced out the charge. How do I fix that formula? I need a second nitrate to balance the magnesium. So I'll put parentheses and a 2 there. Everybody get it? What is the difference between the now purple 2 that I just wrote and the red 2 from our nickel 2 nitrate? Okay. See a couple people shaking your heads no. I'm presuming you're saying there's no difference. And I would make the, at least in my mind, very strong argument that they are entirely different things. The red 2 is to make sure nitrate balances nickel. Why is there a purple 2? The nitrate needs to balance the magnesium. They have entirely different meanings behind why they're written. We can't just copy it down because it's written in one place doesn't mean it shows up in another. Right? There's a meaning behind it. Why is the 3 in NO3 copy across without any problems?
Because you're not replacing it.
That 3 is what makes it nitrate. Right? For the same reason that when we copied across nickel, I didn't write just N. Because if I get rid of the I, it is no longer nickel. If I get rid of the 3, it is no longer nitrate. Kind of makes sense? Okay. The numbers become confusing because we're writing the numbers in the same space as a subscript, but we're writing them with different meanings. Sometimes the number is a meaning of the name. Sometimes the number is the meaning to balance that formula. Okay? So our numbers carry slightly different meanings behind them. You have to realize that meaning to make sure you don't just copy things blindly. Make sense? Okay. We've now predicted our proper products because we've got our proper formula. We can then go through and balance the equation. This is kind of the advantage or the nice thing behind our single replacements. To balance, we'd say magnesium. On the left, I have 1. On the right, I have 1. Nickel. On the left, I have 1. On the right, 1. Nitrate. I have 2 and 2. Everybody see that? That means it's balanced. What would we do then? Check your work. Thank you. My other section's still saying, oh, we're done. No. Check your work. Okay? I don't want to check your work right now. Sorry. I want to move on. We okay with it?
Yes.
Okay. So we've predicted our products. Okay? We've made sure our products are correct. The next stage of a single replacement is decide, did that reaction actually occur? Okay? I can plan out the yin-yang for what I'm going to do when I win $1 million. That doesn't mean tomorrow I'm going to have $1 million to then plan with. What we've done here is planned. We now have to decide, is that actually going to happen? Okay? To decide that, I have to use the activity series.
Magnesium's pretty good.
Okay? And so what I'm going to do is look at the metals that did chemistry. The nitrate stayed nitrate all the way through this, so it didn't really do anything. I'm really concerned about the metals, magnesium and nickel. So I'll go to my activity series and find them. Slowly, because I can't read. Magnesium and nickel. There are 2 interpretations that we can run off of this. Okay. Magnesium is more active than nickel. So I'm now framing around the activity, the increased activity of the magnesium. Because it is more active, it wants to be in a compound. Where is magnesium in a compound in my equation?
All right.
It's on the right-hand side. So now magnesium comes into this situation, and I can be either the left-hand side or the product side as magnesium. And says, well, where do I prefer to be? By myself, left-hand side, or in a compound, right-hand side? I want to be on the right-hand side. For that to happen, my reaction needs to progress towards the right. Does the reaction work? Yes. Kinda? I'm going to guess the head shake no, but then giving me a thumbs up meant you were telling me 2 different things. Okay. So let's flip that, because we looked at the more active one. Could we have interpreted based off of the least active? Sure. Nickel is less active than magnesium. Okay. Because it is less active, it wants to be by itself. So nickel comes into this same question and says, okay, where would I be by myself? On the right-hand side or the left-hand side? Right-hand side, guess what happens? We get the right-hand side. So either way we interpret, either looking at the more active or the less active, still draws to the same conclusion, this reaction should progress forwards. Does that make sense? Is that a yes? Okay. Let's consider our redox now within this. Oxidation state. The oxidation state and charge very often get confused. And I've even talked to other chemistry faculty. They're like, I don't even know why we have to talk about oxidation state. Everything should be charge. Okay? That's because they're kind of Venn diagrams. If we look at charge, that says charge,
Yeah, sure.
and oxidation state, okay, they overlap in a lot of common cases. Okay? So everybody goes through and assumes that oxidation state is the same as charge, just because they overlapped a little bit. Okay? Squares are rectangles. Does that make all rectangles squares? No. Okay? It's how those things overlap. Typically, when we think about chemistry, we don't look at oxidation state. Okay? Because you watch the video, oxidation state has to always be. Okay, let's try a different question. Charge has to always be.
Positive or negative? Neutral?
Nope. We can be positive, negative, or zero. Charge is always given to you. Oxidation state must always be calculated. Why do we typically only focus on the charge? Because it was already given to us. We don't have to think. We don't have to do a calculation. That's where the confusion comes in. Okay? Add to it that sometimes the oxidation state and the charge are the same thing. Everybody go, oh, well, we'll just ignore oxidation state because I don't have to do any work if I ignore it. Okay? If we take a look at the magnesium, I want to look at what's happening here. So our charge is the balance of electrons and protons in the entire unit. Okay, well, what is a unit? Well, it depends what you're looking at. Okay? The oxidation state is the balance of protons and electrons. Oh, crap, it's the same definition. In a single atom. Can an atom be a unit? Yeah. Can a unit be an atom? That's where we run into some issues. Okay? So when I look at magnesium on the reactant side, what is its oxidation state? Okay, well, the oxidation state is solved from the charge. Why would I solve from it from the charge? Well, I'm always given the charge. So I will take the oxidation state of my element times the number of the element, and I'll add that up for whatever my unit is, and that has to equal my overall charge. This looks like a really familiar equation. This looks like the equation that I gave you to use in nomenclature. The textbook just said, oh, I'll just do a crossover rule. Okay? So sure, you could skip and move to the crossover rule, but this equation comes back to haunt you. There's a reason I presented this equation in nomenclature. It's because it's better presented as oxidation state. It allows us to solve. When we go through and solve for magnesium, okay, how many elements do we have in that unit? There's only one. What is the oxidation state? I have to solve for it. Always. Period. No exceptions. It's unknown. Plus, what's the number of the next element? The next element in the unit that is in the blue box. There is none. Which means I stop writing out my equation and I can now write that equal to the overall charge. What is the overall charge within that blue box? Where's the overall charge written? In the top right-hand corner. Is there anything written in the top right-hand corner? What is the overall charge? 0. Okay. The charge for magnesium being an ion would be +2. And you're right. If I wrote magnesium ion, that is what I would write. What is the charge for magnesium ion? +2 shown in the upper right-hand corner. If there's nothing written there, it's 0. So we have to be careful that when we reference magnesium as an element and magnesium as an ion, they are entirely different things. Okay? So will they have the same symbol? They don't. Magnesium ion is a +2. They have the same name. I'm saying magnesium and magnesium. Except you're supposed to be saying magnesium ion to differentiate that. Okay? The other analogy that we could go through with this is sodium ion. Anybody taking a biology class? How do your muscles work? Potassium, sodium, proton, or ion, there's some name for it. What do they call it? Proton? It's not a proton pump though, right? Ion? Sodium ion channels, that sounds better. We're shuttling sodium ions and potassium ions back and forth across the membrane. That's how your muscles work. When you move, guess what's happening? Sodium ion is moving around. So what do we need to exist? What do we need to have in our bloodstream? Sodium ion. Oh, well, I need sodium, so I'm going to take a block of elemental sodium and I'm going to eat it. And I'm now dead. It's not salt. That's sodium chloride. Sodium element has an extra electron that it does not want. So the instant I ingest it, what does it do? Ditch that electron to whatever it can encounter, typically water. Water then reacts with the sodium very violently to produce sodium hydroxide and hydrogen gas. Okay? The sodium hydroxide now destroys the pH balance and I die. Never mind the fact that I've now got hydrogen gas bubbling out of my intestines, okay? Which is also highly flammable. Okay? So it could be a very, very painful death. And yet I need sodium for my muscles to work. But I need sodium ion. The charged species versus the neutral species have very different chemistries. We have to be careful in what we're referencing. That's why our charge is always given to us in our upper right-hand corner. It's always there. What is the oxidation state for magnesium in our blue box? 1 times X equals 0. X equals 0. What is the oxidation state for that magnesium? 0. Okay. We can do the same thing out the other end. Stop visualizing me eating sodium metal. It's not nice. Okay, so let's take a look at magnesium in the product side. How would we go through and solve this? Well, I have 1 magnesium times its oxidation state, which I have to solve for, plus
2 nitrates.
When I'm doing this, these are the number of what? The element. And the oxidation state for the element. Is nitrate an element? No, nitrate is a polyatomic ion. So I want the element. I don't want nitrate. I want nitrogen. How many nitrogens are there?
2.
2. Times the oxidation state of the nitrogen. Whoops, shouldn't be showing X.
Y.
Let's pick Y.
Why?
I was waiting for that to happen. Plus 6 for our oxygens times its oxidation state, Z equals 0. How do I know it equals 0? Look at the upper right-hand corner of what I'm trying to solve. There's nothing written there, so it is 0. Can I solve that equation? Okay. Can I solve it in a way that makes physical sense? No. Okay. We can make some simplifications. Because you watched the video, you know that the oxidation state for oxygen is -2. Why might that be confusing? What is the charge for oxygen? Usually a -2. When we're saying the charge for oxygen is a -2, we're actually saying the oxidation state for oxygen is a -2. So I could make that substitution in here. And this would be a negative 12 equals 0. But I would still get 2y and I would get x. I still can't solve this. Okay? Until I remember one useful bit of information. What kind of bond is connecting the magnesium to the nitrate? This is an ionic bond. Because it is an ionic bond, I can split those pieces into the ions. The ion of magnesium and magnesium nitrate is Mg plus 2. How do I know its charge was a plus 2? So that it could balance the nitrate. Could also memorize it. What is the charge on the nitrate? A negative 1. So instead of solving that x, y, z, now you got me saying z, question, I have 1 magnesium times its oxidation state, and this has to equal the overall charge. What is the overall charge? What is the oxidation state for magnesium? I could go through and do the same thing with our nitrate. I have 1 nitrogen times some unknown oxidation state plus 3 oxygens times a minus 2, and this will equal negative 1 because upper right hand corner it says negative 1. Why did I say the oxygen was a negative 2?
Because oxygen.
That is one you are required to memorize. Oxygen will always be a negative 2. I could go through and now solve. I guess we said that was a y. Y minus 6 equals negative 1. Y equals plus 5. What did we say y was? Don't tell me plus 5. The oxidation state for nitrogen. What is the charge on nitride? Nitride, D as in dog. A negative 3. Why does this oxidation state stuff tend to confuse students? We told you to memorize the charge on nitride to be negative 3. And yet what am I telling you the oxidation state is? Plus 5. It comes out to be something different. Why is it different? One's an oxidation state and one is a charge. Depending on the conditions you're under, you will be looking at either condition. So you have to be careful when you go through to solve to answer the question that's asked, not the question that you find easiest or the question you want to answer. Make sense? Okay, so why go through all of this? Really what I wanted to get to and look at was our magnesium. What happened to the magnesium in the course of this reaction? We went from a 0 to a plus 2. This means you had to lose. Magnesium metal lost 2 electrons in the course of the reaction. Okay? Well, that's obvious, right? When we look at the equation, you see the 2 electrons. What's our symbol for electron? Because I'm seeing some people saying, yeah, I totally see that. E negative. Where do you see an E negative in our equation? You don't. Are the electrons specified in the equation? No. Okay. It is something that we would have to decipher out of the equation. Electrons are never specified in our equations. Okay, why? There's a source of electrons in this room. Anybody know where that source is? There's these little plugs floating around, right? Electricity. And what are we told to do with those plugs? Or really told not to do?
Stick a knife in it.
Stick a knife in them. Why?
They electrocute you.
The electrons are insanely high energy. They pass through you, electrocute you, and you're usually just in a lot of pain. Okay? Yes, experience. Don't do it. Okay? Electrons are insanely high energy and dangerous. Okay? They do not exist on their own. They can only exist in the walls where we have the wires to kind of hold on to them. What happens when you stick the knife in? Yippee! They now come jumping out of the metal through your body so that they can neutralize. Electrons are high energy. They want to be neutralized. Okay? That's why we can use it to generate light or other things or power our devices, because they're high energy. We're convincing them to do something they want to do naturally in that natural flow from high to low energy. Okay? We just take advantage of that. Kind of makes sense? So in our reaction, we're now changing oxidation states. Single replacements, by definition, will always be redox. Right? That sets us up to move into Chapter 17. Okay? This came from the video, so we got the red title at the top. So what I'm going to do is start to slide through these. If you have questions, you need to raise your hand and be like, I don't like how that was discussed in the video. Talk about it some more. Okay? So we've got an example reaction here, okay, showing how calcium gives up its electrons to produce something. This is where we're looking at our oxidation state versus charge. The oxidation state or oxidation number, depending on whoever's mood is talking about it, applies to a single atom. The charge applies to a unit. Okay? And that's the hard part to remember. Sometimes a unit is an atom, but not always. Okay? Modified oxidation state rules. There's more rules to it that you don't want to worry about it. Okay? Know the charges from your ionic compounds. Okay? We need those charges because once we have the charge, we can solve for the oxidation state. So we do need to know our charges. Oxygen will always have a -2. Absolutely have to have memorized. The next one is the sum of the oxidation numbers equals the overall charge on that unit. That's that equation. Okay? The unit can be a compound. It can be an element. It can be a molecule. It can be pretty much anything you want. The element can only be an element. Definitions of charge versus oxidation state. We went through in the video and looked at several solves on what those oxidation states and charges were. Everybody was good with that? Okay, and then we'll just tap that through. Our oxidation states for reactions. Once we know how to identify oxidation states, we then have to apply that to a reaction. So we'll look at the oxidation state for every single element on the reactant side, every single element on the product side, and decide, did it change? If the oxidation state has changed, then we have a redox reaction. Right? And we now have to label reduction or oxidation. Gain of electrons is defined as reduction. Loss of electrons is defined as oxidation. Okay? However you want to memorize that is up to you. I personally go with Leo says Gur. I mention why? Yeah. Okay? That's just easier. Okay? The other one that for some reason a lot of people on this campus favor, I've noticed biology favors it too, which is totally counterintuitive to me. Oil rig. Right? Biology is about what things? Anything that's alive, right? Leo is a lion, right? That's alive. And what do they choose to memorize? Oil rig. The thing that destroys all life. What? Right? This one's in black. This one's in black because I didn't talk about this, I think, in the video. We talk about oxidizing agents and reducing agents. No, okay. Because oxidizing and reducing, you guys got that. You're like, that was easy. I don't have any questions about that, right? I heard a no, so we'll kind of let that slide. We'll also bring in now this concept of an oxidizing agent. Okay? Under the assumption that you aren't reading super fast, what do you think is happening when we look at an oxidizing agent? We would expect oxidation. Okay? We would expect loss of electrons. But guess what happens to an oxidizing agent?
It's stealing.
It gained electrons, it was reduced. Why did we call it an oxidizing agent?
Because
It
it's
causes
layered.
the
Okay. The oxidation agent causes something else to be oxidized. If something else is oxidized, what had to happen to the original? It had to be reduced. Okay? So a reducing agent. Okay? If I'm a reducing agent, I cause you to be reduced. You are gaining electrons. The only way you can gain electrons is if there's a source somewhere. So if I am forcing you to gain electrons, the only way that can happen is if I give you those electrons. So I have to lose electrons. That means as the reducing agent, I lost electrons, which means I was oxidized. Okay? It is very easy to lose track of those. For almost all of the redox stuff, I would recommend, like I do with pretty much everything else, lots of work. Write everything down so you aren't trying to memorize those little switches in your head. Okay? So if we had to identify oxidation states, I think this was on the video, wasn't it? No? Oh, okay, well let's look at the first one then. Because you know me, I got to do the easy ones for myself and make you guys do the hard ones. Let's take a look at the first one. I want to solve for the oxidation state for tin plus 2. Okay? Some people are already jumping to the answer. How many tins are in tin plus 2? 1. I don't know its oxidation state because I have to solve for it. That then has to equal the overall charge for tin plus 2. What is the overall charge for tin plus 2? It is a plus 2. Which means the oxidation state for tin plus 2 is plus 2. Oh, it's the same thing as the charge. Is that always the case?
No.
No. Okay. Set up the work, always solve it out. Oxidation state for iron plus 3. Well, there's 1 iron times some unknown oxidation state. Let's not pick the same symbol. Equals the overall charge, which was a plus 3. The oxidation state for iron plus 3 is, well, plus 3. Okay. You'll notice that I also always say the charge, or that sign, positive or negative, every single time. That is my choice to make sure it's completely unambiguous. When I write it out, I don't write out 3, I write out plus 3. Again, to make sure it is completely unambiguous. For tin plus 4, well, there's 1 times the oxidation number equals the charge plus 4. The oxidation number is plus 4. For iron plus 2, there's 1 times the oxidation number. Should have started earlier in the alphabet. A equals. That was kind of a joke, by the way. Thank you for not laughing and appreciating my humor. I'm not sure that was any better. A equals plus 2. I now have the oxidation states for all of my elements. Now I can apply to see what changed. When I moved from tin to, on the reactant side, to tin on the product side, what happened to my oxidation number? It became more positive. To become more positive, what did I have to do? I had to lose electrons. By losing electrons, I was oxidized. Crap. How do you spell oxidized? I was going to do ation, that's why. Okay. If I was oxidized, what kind of agent was I? I was a reducing agent. Okay. What happened to the iron as I moved from the reactant to the product side? The oxidation number went down. It was reduced. Okay. To be reduced, what happened? I had to gain electrons. If I was reduced, what kind of agent was I? An oxidizing agent. Make sense? Do the next one on your own. We'll leave the last one off. If you have questions, that's one you can self-test at home and then ask me about. So do the next one on your own. Everything we just solved, I want you to solve out. So for that first one, copper all by itself, 1 times A, the oxidation state. That has to then equal the overall charge for that unit. What is that unit? 0. There's nothing specified there, which means the oxidation state is... That can't be a fire alarm. Is that someone's phone? That's way too quiet to be a fire alarm. No, because that would be flashing. And that first one is 0. We move to the next one. This is where a lot of people got stumbled. Okay? The oxidation state of each element added together must equal the overall charge for nitrate. The overall charge for nitrate is -1. I now have 2 unknowns, B and C. How do I solve? C is -2 because oxygen is always a -2. I can now set it up as B minus 6 equals -1, and I get B equal to +5.
Yes.
Okay. Copper on the product side, 1D equals +2, because we're looking in the upper right hand corner, it's a +2. So that means D equals +2.
I like this swap.
The final product, NO2, 1E plus 2F equals 0. There is nothing written in the upper right hand corner, so it is a 0. F, by definition, is -2. I can substitute in E minus 4 equals 0. E equals +4. If we go through to evaluate, what happened to our oxygen? C to F. Stayed the same, so it's not redox. What happened to our copper? It gained 2 as far as its oxidation number, which means it lost 2 electrons. I'm guessing that's why you were like, no. We went from a -2 to a -2, so nothing changed to the oxygen. Okay, so remember, when we're looking at our oxidation states, we're only applying to the element. I haven't looked at the nitrogen yet. So we gained 2 in our oxidation number, which means we lost 2 electrons, which means we were oxidized, which means it was a reducing agent. The instant you see ing, you should panic a little bit because that's saying it's doing the opposite. The other one is ant. Sometimes it'll be referred to as a reductant. Why? Because English. Okay. If we take a look at our nitrogen, we went from B to E, +5 to a +4. What happened to our number? Okay. It went down, so it was reduced, which meant gain of electrons. If it was reduced, it was the oxidizing agent. Because I have a little bit of space here, that could also be written as the oxidant, ANT. You see ing or ANT, that's when you have to be like, okay, that's meaning it's asking for the opposite of what's happening in the question. Notice all the work that's written out there. Is that something you could internalize? Arguably determine the oxidation states, yes. The rest of it, I would show all the arrows to connect. One of the added benefits, I have colors. Do you have colors?
No.
You could. Right? If you want that, get some colored pencils and use that on the exam. I don't have any problems with that. That doesn't hurt me. Okay? Use it in your homework to make sure that you can get those parallels tied so you can get the correct answers. Make sense? Okay. So a couple interesting questions come out of this. I went from a +5 to a +4. That means I gained how many electrons? 1 electron. I went from a 0 to a +2. That meant I lost 2 electrons. Are my electrons balanced?
No.
No. That means the equation I'm looking at is not a balanced equation. Do I need to have a balanced equation to determine oxidation states?
Yes.
No. Okay. It is not necessary. We already determined the oxidation states is not a balanced equation. Okay, so if you're being asked about oxidizing and reducing and all that fun stuff, you don't have to balance the equation. Okay? But could I then ask for you to balance the equation? Yes, I could potentially. Right? And if we went back, we could look at it and say, is it balanced? Do we have to do all of this work to figure out it wasn't balanced?
No.
How many oxygens on the left-hand side? 3, and on the right? 2. The oxygen isn't balanced. You will have a very hard time balancing that question. Okay? I would argue you won't be able to do it, period. Okay? So how would we go through and balance? Okay, well, so, yeah, a bunch of answers if you were curious. There are certain cases that when we look at a redox reaction, they are trivial to balance. This one, for instance. Okay, why is it trivial? Well, how many zincs do I have? 1 and what? 1. Remember the 2 is the charge. Okay, how many hydrogens do I have? 1 and 2. Is it balanced?
No.
What do you need to do? Put a 2 in front, right? Now it's balanced. If we went through and looked at our oxidation states, we would find out that, sure, yep, everything's balanced. We transfer 2 electrons, everything's golden. So it worked. We didn't have to do any oxidation state stuff. Other times it may appear trivial, but is not. How many tins do we have on the left? 1. On the right? Iron's on the left. 1 and 1. That sure looks like it's balanced. Okay. However, there's one more piece that we have to be thinking about when we go through to balance. The charge. What is the charge on the left? Okay. So lots of answers just came flying out of there. If I ask for the sum of the coefficients as written, what is it? 1, 1, 1, and 1, I'd have 4, right? Okay. But when I ask for the charge, I'm getting people telling me that it's +2. What is the charge on the reactant side of the equation? It's a +5. I have positive from both the tin and the iron. The charge on the reactant side is a +5. I have to account for all of them. You okay there? How about on the product side? Is the charge balanced? No. For an equation to be properly balanced, the charge must also be balanced. To do that, we have to deal with our electrons and deal with redox. Okay? That's where we encounter other rules on how to go through and balance. Okay? To do this, it is usually easiest to split it into the half reactions and balance each half reaction independent of the other. So what would our first half be? Well, what's the first element you see? Tin plus 2. So tin plus 2. Okay? There's only 2 reactants, so I'm going to ignore the other reactant. Okay? Because if I did tin plus 2 plus iron plus 3, how do I balance that now? That becomes really hard to balance without adding more elements, so that doesn't work. So I'm just going to look at the tin plus 2. Tin plus 2 looks most like iron, right? No. Okay. I appreciate the subtle sarcasm in that statement. Okay. Looks most like tin plus 4. Is that equation balanced? No, the charges don't match. Because this reaction cannot run on its own, it has to be run in partner with another one. I now have the added benefit of adding things into this equation that don't normally exist, like electrons. How can I add electrons to get this equation to balance? What's that? Add it to +4. So I'll add an electron over here. What's the charge become on the left-hand side? It should become a +1. Did I get closer to it being balancing or further? Further. So did I place the electron in the right spot? No, that was a bad idea. Where should we add it? Add it to the other side. I know that's what you meant, but I was being a jerk. Okay. What's the charge on the product side? +3. Are we closer to the charges balancing? Yes. Are we there yet?
No.
What do you need to do? Add 2 electrons. Do the charges now balance? Yes. I've now balanced 1/2 of my reaction. I'll go through and do the same thing with the iron +3. Okay? When I do the iron, I only need 1 electron, not 2 electrons. So if I now added these 2 reactions back together, what would I get? I'd be left over with a surplus of 1 electron. Well, now the charges would balance, the elements would balance. But what's the problem with that equation? We have an extra electron. Electrons not stable, they can't show up in our equation. Angry little devils. Which means somehow or another we have to go back and ensure that when I add those 2 equations together, that the electrons cancel each other out. How can I do that? Well, let's ignore that. How can I do that? Yeah. Let's times the top equation by 2. Okay, what are we saying by timesing by 2? We're running that reaction twice. When we're looking at our chemical reactions, we kind of get locked into, oh, we're just running it once. If we change the coefficients, we're saying we need twice as much of that to run. We are doubling it, okay, or tripling it, or quadrupling it. That's exactly what's happening here. So if I multiply that top equation by 2, what happens? Well, now I don't have 1 electron anymore. I would have 2. I don't have 1 iron +3 anymore. I have 2. I don't have 1 iron +2 anymore. I have 2. Now when I go through to add the equations together, what happens to the electrons? They would cancel. The result is that I have 2 iron +3s, 2 iron +2s. This equation is now correct. Well, as with all equations, we should be able to check our work. How many tins do we have on the left? 1. On the right? 1. How many irons on the left?
2.
Irons on the right?
2.
2. Everything's looking pretty good, so now let's move into the last one, charge. What is the charge on the left? Well, the tin was a +2. The iron was a +3, but there's 2 of them. The charge becomes +8. Everybody see that? How about on the product side? Tin was a +4. Iron was a +2. There's 2 of them. And I get, does my charge balance? Yes. What does that mean about my equation? It's now balanced. That is the half reaction method. We split our equations into just reduction or just oxidation. We balance those out using electrons. We then make sure that when we add the equations together, the electrons cancel. Okay? We'll make sure the electrons cancel by multiplying one equation or the other by some value to make sure that the electron numbers are the same. Kind of similar to what you did in nomenclature when balancing out formulas, determining the subscripts in your formulas. It's pretty much the exact same process. Okay? So there's a bunch of work. Whoop! Come back here. So use the half reaction method to balance that last one. You'll notice that last one does, yes, use the half reaction method to balance that last one. You'll notice that last one should look mildly familiar. What does that one look like? It's the one that you just went through and determined charges and oxidation states and all that fun stuff for. Okay? Except I added water and H+. Don't worry about why you need water and H+, but you need them. Balanced by half reaction method. Do you guys want a hint? No, I heard a no. Okay, so for the person that said no, don't look at the board. For people that say yes, I'll give you a hint. And in some fairness, it's a pretty crappy hint. Here's the first half reaction. That was it. Plus 2, that's 1/2 of the equation, which means the other half is whatever's left over. Okay? In that other half, we have a lot more pieces. Completely irrelevant. I have to include all those pieces, right? Because it's halves, so I only get 2. Right? You'll notice I've shown a +5 going to a +4, and I'm pointing those arrows at nitrogen. I didn't show any work for that. Where's all my work for that? Like 2 slides ago, 3 slides ago, where we showed all that work for determining the oxidation states. You would need that information to be able to look at this. So +5 to a +4. Okay, by looking at those, I know I need an extra electron on the left-hand side to balance that charge out for the nitrogens. Arguably, I don't even need that information. But I also don't need that. What else could I do to figure out that I need the electron on the reactant side? What is going on with my charge there? That's not balancing out my charge nicely. What happened? No, so I lied. I was completely wrong there. You do have to look at the nitrogen. Sorry. You have to do the oxidation states. Right? Would our equations, if we added these 2 up, now balance out? No, we have 2 electrons as a produced and only 1 electron consumed. We need to make sure that balances. How do we do that? We'll multiply that bottom equation by 2. So how many electrons do we then have? 2. How many hydrogens? 2 nitrates. 2 waters. 2 nitrogen dioxide. 2. Now the electrons would cancel out. Now what can we do? We can add it all together. Copper plus 2H plus 2 nitrate. Go to copper plus 2. Oh, I remember what went wrong with this one. 2NO2 plus 2 H2O. Yeah, I know exactly where this one becomes a problem. We're going to kind of leave it hanging on that one. This was a poor example, but we've balanced out our electrons to make sure they add across. The elements currently balance, okay, and we'd have our correct answer. Okay, and I'm going to slyly step away from that because there's a pretty big mistake in there that I'm going to ignore for the moment because the methodology was the important part behind that. We've got more practice here. I'm going to turn this practice into a quiz on Monday. So I want to know how many electrons were transferred. Okay. It'll be a relatively straightforward quiz. Okay. Because what I'm going to do, well, actually no, it'll be a relatively straightforward quiz. I will give you 5 minutes. And that really 5 minutes is me passing out the quiz papers and then collecting the quiz papers. Okay? It'll be this exact question. That will be the quiz. The question will be how many electrons were transferred in the course of this reaction. Okay? And then on Monday we'll work through it to get to the correct answer. Assuming also I didn't give you the answer. Good, I didn't. Okay? You should have to go through and do the half reaction method for this. If you have questions about it, by all means, talk to whoever you want to. Talk to tutors, talk to me. More than happy to help you with it. Okay? But I need to make sure that you go through and do it. Okay? The next part is our double replacement reactions. We did the first one. We also did the second one. We did that in trying to identify our reactions. So you should be able to get those two formulas, or those two equations established, which are not quite balanced. How can we balance them? As a hint, it's the first one that's not balanced.
K2, that's one.
We have a K2. So we have 2 potassiums on the left-hand side. How many potassiums on the right? Only 1, so it's not balanced. How would we fix it? Put a 2 there. Believe it or not, that's all you need to do, and that equation is now balanced. Okay. The bottom one is balanced. Okay. The big part that becomes challenging with our double replacements, not only do you have to be able to predict the products, balance the reaction, but you also have to be able to specify the phases. Okay. Note for the top one, I'm saying barium chromate is a solid. Nowhere in the question does it say anything about barium chromate. Nowhere in the question does it say anything that it should be a solid. For the bottom reaction, both of your products are aqueous. Meaning, was there a chemical reaction? No, no change in phase, no chemical reaction. The better answer for that one would be no reaction. I'm just saying nothing happened. Okay? It's easier to say nothing happened once you evaluate what the potential something was. All right? How do we decide those phases? That is our solubility rules. Okay? The solubility rules are listed out nicely in your textbook. You could go through and apply those rules to every single species within here. All right? So let's start with barium chloride.
Oh boy.
What I need to do is find in that list either barium or chloride. Which do you find first? Okay, that's fun. I heard both. I heard someone say chloride. Where do you see chloride? What rule? Rule 4. Someone said yes to barium. What rule? Uh, 9 has barium in it, but it has barium sulfide. 10 has barium hydroxide. Does barium show up?
No.
Arguably, barium does not show up. There is no rule directly referencing it. So we need to look at just Rule 4. What does Rule 4 say? Rule 4 says halide ions. Oh, that's useful. What is it referencing? The header of that, which says ionic compounds containing the following ions are soluble in water, which means they dissolve. We specify that solubility by writing AQ for aqueous. Insoluble we would specify as solid most commonly. For everything they've listed here, it's solid, but sometimes you'll see liquid. And you could potentially see gas, but that one's kind of a long shot. Right? So, Rule 4, halide ions fit under the generally soluble, except, crap, we've got exceptions. Is barium one of those exceptions?
No.
No. What does that mean?
Don't worry about it.
Not don't worry about it. We still have a conclusion. It's soluble. So the phase for barium chloride is AQ. Look at that. Somebody wrote that something correctly. Let's jump to a harder one. How about barium chromate? We just looked for barium and saw that that barium does not show up. So that's not very helpful. Okay. So we need to look for chromate. Where does chromate show up? Rule 7. Take a look at Rule 7. It says chromate ion. It's referencing the header of that. Ionic compounds containing the following ions are generally insoluble, which means it should be specified as a solid. Okay. Chromate ion is generally insoluble, so it should be a solid. Unfortunately, we also have that little floater in parentheses saying exceptions. See Rule 1. What is Rule 1? Alkali metal ions, which happen to be the first column of our periodic table. Is barium in the first column? No, so we don't worry about the exception. Barium chromate will be a solid. The phase is correct. Okay. So to be able to interpret those phases, what did you need to have? The solubility rules. Are you given the solubility rules on the test?
Yes.
You're given a condensed form. So if you take a look at your exam, there are like 2 solubility rules listed on it. So for the semester exam, yes, I give it to you. For the final exam, I do not. Okay, the final exam, you are not allowed any extra information. So I would recommend that you spend some time memorizing. Okay, when it comes to the solubility rules, there are only 3 I have memorized. Which 3?
1, 2, and 3.
1, 2, and 3. Why did I pick the first 3? Okay, we could say I'm lazy and I can only count that high, so I picked the first 3. Not quite that bad, but most common. They do show up a lot, but I would argue chlorides show up a lot too. Take a look at the top 3. Do we see parentheses with the top 3?
No.
Why not?
There's no exceptions.
There are no exceptions. Why did I memorize those 3? Because there isn't an exception to my memorization. That's when I memorize. Okay, and that's the only time I'll memorize. Okay, so those 3 I would highly encourage you to memorize, though again, it is not an absolute requirement for the semester exam. It will become important for the final. Okay, our neutralization reactions are double replacements. All you're doing is exchanging it across. The one thing that you're getting here is water produced. So water and a salt. Last one is our combustions. This one was a beast to memorize. We'll go through and do this one as a balancing after we do the quiz on Monday. With that, ignore that statement. That's a bunch of review stuff. With the rest of that, we're just talking about facts that you probably already know or have already been using for doing all the other content that we've talked about. So Monday's lecture should be mostly kind of easy review stuff. If you have questions, that is an awesome time to bring those questions up because the exam is next Wednesday. Okay? Thanks.